Hi, again. So all along we've been talking about electromagnetic fields and how an oscillating electromagnetic field produces light. And that light is going to travel in waves. And all of the effects that we've talked about up to this point have been entirely due to waves. Well, could matter also be a wave? And that led to some very important results in the world of physics and eventually into quantum mechanics. Well, once they discovered that, yes, matter actually is a wave, and we're going to see why that's true, and that's a little weird. But then, could light, if matter is a particle and a wave, could light also be a wave and a particle? And we found out that's true as well. So, what we're going to get into in this lecture is we're going to find out exactly why that's true, or at least the experimental evidence behind why that's true. And then we're going to see what consequences are going to result from that. Let's get started. All right, so let's see what we have here. So, we've been talking about light being a wave. So let's say I have light that's shining on two slits. We'll switch to our pen here. So this will be our light source, and it's putting out a wave. And that wave is shining on two slits. Like that. There's one and two. So this, of course, is a wavefront. Can light pass through both slits at the same time? Sure, we've seen that all along. So yeah, it absolutely can. Now, what if instead of having a wave, a light wave, what if I had a paintball gun? So I've got this little paintball launcher and it's sending paintballs. Can a single paintball go through both slits at the same time? Well, no, that'd be crazy, right? There's no way that it can be in two places at one time. So this property fundamentally defines the difference between a wave and a particle. If it can go through both slits at the same time, it must be a wave. If it cannot go through both slits at the same time, it can't be a wave. And so that if it can't be a wave, then that's what we're going to call a particle. Now, you've learned in the previous semester, particles have mass and energy and momentum. They collide, they interact, all these other things are going on. Light doesn't have mass, but it does have energy. And as you've probably seen, we do know that E equals mc squared. So the energy and mass are actually two forms of the same thing. So could there be a relationship between that? And it's obviously interacting by producing these fringes, right? So take a look at microtest 2 then. Suppose that instead of using paintballs, we use tiny objects like electrons. So ones that can easily just, fire straight through, but they're still going to be particles, right? They're still going to be tiny little particles. So what kind of pattern would you expect to see from the particles, the electrons being fired at these two slits right here? Pause the video, think about it, draw what you think you'll see. Well, you probably would predict that if this was a screen, get, a bunch of electrons over here and a bunch of electrons over here. That would make sense, right? So, as the electrons fire, some of them are going to go through here and some of them are going to go through here. In no case will I get them to go both, so there's no way that they can interfere. What's interesting, though, is if we actually do the experiment, this is what we see. So we start out by turning the electron beam down really low, which means we're not getting many electrons per second or anything like that. And so this is the picture that we see. Draw my pointers here. So with this picture, we're only seeing, just a few electrons hitting the target. And they seem to be fairly scattered throughout, which is what you would expect, right? They're either going through this hole or they're going through that hole. As we start turning up the power in the beam, then it starts getting more and more random. We start getting more of these things. They're still pretty much all over. But over time, if we let the beam run for long enough, this bottom one right here, this is the pattern that we start to see. Does that look familiar? Where have we seen that before? That is the double slit interference pattern. Exactly like what we saw with light. So you have bright bands and you have dark bands. Now, you might think, okay, wait a minute. There's absolutely no way that particle was in two places at one time. How could they possibly interfere? And it is true that the electron is a particle. It did not go through both of these slits at the same time. However, there seems to be a probability that the electron will either go through the left slit or go through the right slit. And not only that, there seems to be that probability by the time it gets to the screen, those two probability waves interact with each other. And so there is a greater probability that the electron will hit in one of these areas than there is in the darker areas. So the electron is not what you might want to think of as, somebody broke apart the electron and it's actually waving through. No, but the electron has a probability of where it can be. So the beam of electrons acts as a wave over a long period of time. The particle, over a short period of time, the particle is a particle, and it is a particle, but it has characteristics of both. There's no other way to conclude from this that the electron has particle characteristics. It absolutely does. But over time, when I can build up a beam to where it acts like a wave as well. So this is called the wave-particle duality. So basically, it's that the electron can be treated as a particle or as a wave, and which one kind of depends upon the situation from that. This is the foundation of quantum mechanics. Quantum mechanics is really about probabilities, and we can't know exactly where that electron is going to be. And one of the uncertainty principles is that if I know its energy, I can't know its position. If I know precisely its position, then I can't know its energy. So there's a limit to what I can know. So all I can say is, well, probably it's in here. And so I might say, I can draw this probability distribution that looks like this. And I can say, okay, this is the probability that it's going to be somewhere along this position. And yeah, it's most likely to be there. But it might actually be, there's a small chance it'll actually be over here, and there's a small chance it'll actually be over here. So now when I start interacting with these two different probabilities, they start to interfere like waves. So we won't be doing quantum mechanics in this course, obviously, but this is going to be the foundation for what you'll be doing for some of your later coursework. All right, let's shift over to the next page here. So if electrons can act as a wave, and by the way, all matter, their electrons make up all matter, so there's no reason why the rest of matter couldn't either, then they must also have a wavelength. So in 1924, de Broglie is how you pronounce it. It's not de Broglie, but it's de Broglie. He proposed an expression that would give us the wavelength of this. And let's zoom in on that here. Basically, remember that it mattered how long the beam was running, and it mattered how much energy was in the beam. And so the wavelength must be related to the momentum of the particle. So because the momentum, of course, is related to the energy. And so this gives us an expression that we can use for finding that wavelength. And when we say wavelength, again, we're talking about the probability wave that's coming in. So lambda is the matter wavelength. H is the Planck's constant that we've been using, and then P is the momentum. So we'll zoom back out so we can see this part. There we go. So do you remember the mathematical expression for momentum? If not, go through your flip book. But yeah, it's P equals the mass times the velocity. All right, so let's look at the scenario then. We've got everything that we need. Let's see if we can find out the wavelength of this particular particle beam. So here we've got, this is the mass of a single electron right here. Now we have a whole bunch of electrons, but so the only reason we can see this is because we have trillions of electrons. Remember, when we only had a few, you couldn't see the pattern. So we're going to assume that the beam has them traveling at about 6 million meters per second. So that's all you need. Tell me the wavelength of this light, of this electron. All right, so what we want to do is we want to find the wavelength, the de Broglie wavelength of this electron beam. Notice that we can't really say the wavelength of an electron because it depends upon how fast it's moving. It depends on the energy it has. It depends upon the momentum really that it has. So we have to also specify the beam, the velocity of that beam that's coming in here. So the procedure is pretty straightforward. we're going to combine the momentum equation with the Boyle wavelength equation. And that's really all that we're going to have to do. All right, let's flip over to the next page then. All right, so reminding ourselves of our quantities then. We're going to put them here. So we know that the mass of the electron is going to be 9.11 times 10 to the 31, 10 to the minus 31 kilograms. And then we know that the velocity is going to be 6.0 times 10 to the 6th meters per second. And then finally, Planck's constant is going to be 6.626 times 10 to the minus 34 joules per hertz. Our equations then, we know we need the de Broglie wavelength equation because that's what we're trying to find, h over p. And then from first semester, we know that p equals mv. All right, so let's put this in then. Always combine what you've got before you start plugging in numbers. Unless they actually ask for the momentum, don't figure it out separately. You're just giving yourself another chance to make mistakes. So I've got h over m times v. And so that's going to be 6.626 times 10 to the minus 34 joules per hertz divided by our mass, which is 9.11 e to the minus 31 kilograms times the velocity, which is 6.0 times 10 to the 6th meters per second. Punch that in your calculator and see what you got. So when you do all the math, you should work out that the wavelength is going to be about 0.0121 nanometers. So is it possible to manufacture a screen that's about this far apart? Sure. I mean, we work in nanometer scale things all the time. A simple diffraction grating that you can make very cheaply is going to be on the order of nanometers. So this is definitely something that's easy to do. So it's very easy to see the wavelength of small particles like electrons. We can see them interfere simply by having them pass through firing this beam at this double slit apparatus. So then the question is, why don't we see that with paintballs? So let's use this same result that we found, and let's assume we have a 3.2 gram paintball moving at 20 meters per second. All right. So we're going to take the same expression. And so I get h over mv. And that's going to be 6.626 times 10 to the minus 34 joules per hertz. And again, we need to be very careful with our units. That's a 6. So it's 3.2 grams. So that's 3.2 times 10 to the minus 3 kilograms. And then we have 20 meters per second. So pause the video and punch that in your calculator and see what you get. Ready? You should get about 1.04 times 10 to the minus 32 meters. That's kind of insane. Is there any chance, since a paintball has a diameter of about 2 centimeters, is there any way it's going to fit through a slit that size? Even if you could manufacture something that small, the paintball literally cannot go through the slit. So there's no way to observe these probability waves, these matter waves, with a macroscopic object like a paintball. You yourself are a wave. However, the wavelength is so short that we're never going to be able to observe the wave-like functions of your own body, your own matter. Okay, so let's take this next picture. Is kind of interesting. And we'll zoom in on that so we can see what we're doing here. So we can use this technique then to observe small atoms. Electron microscope uses the wave nature of electrons to observe tiny, tiny, tiny objects all the way down to atoms. So an electron microscope doesn't actually use light like you would expect from our standard microscope, because the wavelength of light is much longer than an electron. We saw what the electron beam was, and it's an order of 10 to the 4th or more. So However, if we use an electron beam, now we can start to see individual atoms. And that's what you're seeing here. In this picture, each dot you see is one atom. And then IBM has developed some techniques where they can move around these individual atoms, and that's what they've made the picture with from this. But it's kind of bizarre to think about seeing atoms. I mean, no, you can't see them with light, but you can see them if you can choose some sort of observing mechanism that has a short enough wavelength. And electrons can do it because they are, in fact, waves. Okay, so as we said, since matter, which are particles, can act like waves, could it be that light can also act like a particle? And it turns out that it does. Let's see if we can get an idea of how that might work. So in this way, we're going to do an experiment, and we're going to shine that light through the slit. Okay, so just a single slit, just a tiny pinhole. So here, that's what we're showing you here. And so when the beam is at full intensity, you see exactly what you expect you would see. There's a bright spot that kind of fades to black evenly on all sides. And you've seen this, probably every day of your life almost. So now suppose we're going to put a filter in there that's going to block out 50% of the light. And that's what you see here. The image looks basically the same. You've still got that brightest, may not be as bright because we blocked out half the light, but you've got that brightest spot in the middle, and then it fades out evenly on there. So before you go on to the next page, what would you predict to happen to the image if we kept cutting the intensity by 50%? So we take another 50% filter on there and we cut it to 25, and we put another one on there and we cut it to 12 and a half, and so on and so on. What do you think is going to happen? Let's go ahead and jot down some ideas. Try to commit to it. Well, this experiment has been done, and it's actually an experiment you could do if you have enough filters. But interestingly, this is what you get. It starts to look more and more like individual particles hitting the screen. If light is a wave, you should never see these little pinpricks, right? It's just a wave, like an ocean wave, that's just moving into shore. So, and then as you can see in the bottom picture, as we decrease the brightness even more, now the effect is even more pronounced, and you can tell that there are absolutely individual particles of light. And yet it behaved exactly like a wave when it was at a higher energy and higher intensity. So this is another example where we have something, light, electromagnetic field, that is displaying both wave-like behavior, the interference pattern that we see when we have single slit diffraction, for example, and particle behavior, like you see here, where we have these individual particles that are being scattered throughout. So let's zoom back out here. So the only way to explain that is that light is both a wave and a particle. So the name we give these light particles is a photon, and you may have heard of it, even from Star Trek photon torpedoes or whatever, but a photon is a light particle. Keep in mind, it is still a wave. That particle is still an oscillating electromagnetic field. It's not something distinct from what we've been talking about. It's just that it acts like a particle in some situations. And to really get into why this is true, that's when you have to get into quantum mechanics. But for our purposes, though, one of the most important things that we need to understand is that photons can't be divided any further. They are the smallest little quantity of light that we can talk about, even though they are waves, don't forget. So that if something can't be divided any further, then we say that it is quantized. So it's 1, 2, 3, 4, not 1.5, 2.5, so on and so on. And so that's where the name quantum mechanics comes from, because it is quantized. It can't be divided into any smaller pieces. So if the particle is if the light is a particle, it's got to have both an energy and a momentum. Well, we've already understood that it's got energy. We know how to calculate the energy because it's the energy of the electromagnetic field. But what about the momentum? So take a look at our definition here. Here's our usual definition for momentum. P equals mv. And that works fine for everything. But light has no mass. There's no matter in it whatsoever. So this would mean that it has no momentum, right? But if you have energy, you also have momentum. You can't have one without the other, as we saw in the first semester. So we have to come up with some way that we can define momentum maybe a little bit differently for a light product. And so we can define it by assuming, that's what we say here, the wavelength of the light is equal to its de Broglie wave. And if you think about it, that makes sense. It's once we get down to this de Broglie wave level, that's when we're getting this idea of this wave-particle duality. And so also when we think about electrons, the de Broglie wavelength depends upon its momentum. So that's going to give us our best place to start. So flip over to the next page then. And let's see if we can come up with a mathematical expression for the momentum of a particle. And so work with me on this. So we need a definition that does not involve mass, and we know that we're going to use the de Broglie wavelength. So first of all, let's start out with what we know. We know that lambda equals h over p, right? The de Broglie wavelength is Planck's constant divided by the momentum. So let's solve that for p. So we get p is equal to Planck's constant over lambda, okay? Now we also know that the wavelength is related to the light's frequency. The light has a wavelength. It is a wave. So let's put down our expression for the relationship to the frequency. So we know that that's going to be c over lambda, right? And let's use that then in our expression here. So I'm going to solve this for lambda. And so I get lambda is c over f. Let's put that in up here. And I get that p equals h over lambda means that that is equal to hf over c. Just like that. So far so good. Now we've written the momentum in terms of the frequency, but let's get it in terms of the energy, because it's very easy to talk about the energy that's contained in it. Remember, that's actually what's happening. It's an electromagnetic wave, so it's got energy contained into it. So we need to use the Einstein-Planck relation. So E equals hf, like this, and we get something really nice that tells us that E over C is equal to P. And we made the comment here, this relationship is what made Einstein realize that light was both a wave and a particle, and that matter and energy must be two forms of the same thing. Because if light is a wave and light is a particle, meaning it's got mass, meaning it's a mass, it's matter, then this must be two forms of the same thing. It just happens that light is a case where all of that mass energy is in the energy flavor, and none of it then is going to be in the mass flavor. So there are, you may say, well, okay, that's great, but who would ever do anything with this? Well, if you've ever heard of a solar sail, this is actually how a solar sail works. So let's look at the microtask here, at the scenario. Let's flip over to the next page. And what's happening is this. Let's erase this real quick. What's happening is this. So say I've got a mylar sail right here. And mylar is what we make happy birthday balloons out of. Okay. But let's suppose that I've painted it black, so it is perfectly absorbing. So it absorbs all of the energy that comes into it. And I've got the sun over here, and it's sending out energy. And so that hits here. And that's what we've got shown in the picture that you see right here. So we want to know what is the force of the sun on a perfectly absorbing black sail with an area of 1 square kilometer. Okay, well, to do that, we have to know how much energy the sun's putting out. The intensity of the sun, the intensity of the energy put out is 130 or 1360 watts per square meter. This is called the solar constant. And this is the power per area. That's the power per area that it's putting out. All right. So we want to know what then is the energy that's going to come out of this. So let's start keeping up with our symbols here. So our plan. So if it's absorbing, right, then all of the momentum goes into the sail, right? So the energy is going to be the power over some time interval dt, right? And then force is just going to be, this is capital P power. The force is going to be lowercase p divided by dt. So my change in momentum, so dp dt is going to be my force. So when we have an expression for finding the energy now, so let's use that. Let's see how we do it. Okay, so we have that the solar constant, the intensity, is going to be 1360 watts per meter squared. We're told that the area of the sail is 1.0 square kilometers. That's a big sail, but not unreasonable. It can certainly be done. We don't know the power of the light in watts, and we don't know the momentum of the light in kilogram meters per second. This is why putting those units here is really helpful to help you distinguish between these letters with that. We're also going to need to find the energy, and that of course is measured in joules, and the force, which is going to be in newtons. And then eventually we may even want to figure out how fast it's going to go, but we'll worry about that in just a little bit. Okay. The only other thing that I'm going to need to know is the speed of light, and you know that that is 3.00 times 10 to the 8th meters per second. All right, so we've got all the data that we need here. So you have, as usual, you guys have a place where you can work it on the next page. I'm going to just put it over here in the margin so that we can still keep everything up where we can see it. So our equations then, we've basically got them already lined up. We know that the power is going to be the intensity times the area, because the intensity is just the power divided by the area. We know that our change in our energy is going to equal P dt. That change in energy, that's how much energy is being transferred to the sail. Make sure that makes sense to you. And then our change in momentum then is going to be dE dc. Make sure you see why. That's because P equals E over C. Well, we need to take the derivative of both sides. C is a constant, so that becomes dP. dP is dE over C. Okay. And the reason we need that derivative is because in order to find the force, I need dP dt. And hopefully you're going to see that those dTs are going to cancel. And so we're going to have a constant force going. It's not going to be a force that's time dependent. That's going to be important for what making solar sails even be useful. Okay, we've got what we need. Let's put them together. Let's see what we can find. We've got 4 equations and 4 unknowns. So we'll start with what we're actually looking for as usual. So that's dP dt. We know that dP is dE dc. So let's put that dE over c, that is. So let's put that in there. So we get dE c dt. Like that. Next one, we're going to substitute in for dE. So F is going to be capital P dt over C dt. Of course, that cancels out and just leaves us with P over C. And then finally, we're going to substitute in for the power. And so that gives me the intensity times the area of the sail divided by the speed of light. And there is our general expression for the force on a solar sail. If it's completely black, it's absorbing all of the energy that's coming in. So now we want to plug in our numbers. And so let's see, we have that I is going to be 1360 watts per square meter. We have that our area is 1.0. Now it's 1.0 kilometers squared. So that's e to the third times 1.0 e to the third. Lots of people are going to get confused with that because we've got to convert this to meters. Be very careful with your signs. How many of you forgot that? It's common, but you got to be careful. You're going to be off by a whole lot. And then finally, we have 3.00 times 10 to the 8th meters per second. So you do all that and you do the math, and we get 4.53 newtons. Well, 4 newtons is about a pound, roughly. So that's not a lot of force. 1 pound is not going, certainly not, 1 pound of force is certainly not going to lift something off the surface of the earth. However, if you're already significantly outside of the gravity well, and this force is constant, then that means I have a constant acceleration. Because remember, my acceleration times my mass is my force. So my acceleration is just the force divided by the mass. So if I can make the mass of my sail very small, then I can actually get a decent acceleration. And here's the thing, it's free and it's constant and it's forever. And so we can build small little spacecraft, small little space probes that can reach a significant fraction of the speed of light in just a year or three. So that's the power of solar sails. None of them are very fast, but it's a constant force out in space where I'm not being interfered with. I don't have any other forces interacting with me, and I can just take advantage of that constant acceleration. Now, I can do a little bit better than this. Let's go to our next page. So what if I didn't paint the Mylar black? So Mylar, remember, is kind of it's actually a metal, but you see it in happy birthday balloons, things like that. You can kind of see through it. But the Mylar sail reflects, suppose that we've got Mylar that reflects all of the light directly back. How does things change? Pause the video and think about that. So now instead of just absorbing it, I'm reflecting it back. Well, remember conservation of momentum. When that particle, so if this is my sail, that particle provides some momentum this way. It originally had this momentum going in that leftward direction. When it comes back, so let's say that this is in the positive direction. When it comes back, it's got a momentum in the negative direction. But conservation of momentum then says that this must get, the total must equal zero. So the P of my sail before plus my P of my light before must equal the P of my sail after plus the P of my light after. Well, P of sail before was zero. These two, this was, if we call that positive P of the light before, and this is the P of the sail after, then this was negative the light of the sail, the momentum of the light before, right? Because it went in positive and came back negative. Bring that over to the other side. And that's a P. I don't know why it's looking like a B. There we go. Then I'm going to solve for this. So that tells me, let's just rewrite that a little more cleanly. 2PL before. So that tells us that we get twice as much momentum by making it highly reflective because of conservation of energy. So you may think, oh yeah, I want to make it black so it can absorb all that energy. No, you'll actually do better if you reflect all that energy straight back, because of conservation of momentum now means you're getting twice the momentum from a single photon. So we can make maximum use of that. Okay, so then the question that we have here then, suppose, let's flip over to the next page. So suppose we've got our starship and it has a mass of 20,000 kilograms and a Mylar sail that has a mass of 5,000 kilograms. So the total mass of the spacecraft is 25,000 kilograms. How long would it take to reach a speed of 1 kilometer per second from rest? And so we're going to use this acceleration that we found before. So we found, for our expression, just to remind you, we found that the force for, if it's only reflecting, if it's only absorbing, we found that that was going to be, whoops, we put the I first, we'll just keep it that way. It's going to be I times A divided by C. But if it's perfectly reflecting, if it's Mylar and it's reflecting it back, then we get twice that much because we're getting twice the momentum. So my total force then with my Mylar is going to be 2IA over C. All right, what we actually want though is the acceleration. So we know that the acceleration is F over M. So my acceleration then is going to be 2IA over MC. Okay, now we want to figure out how fast is it going, or how long will it take to reach a speed of 1 kilometer per second, which is pretty, that's cooking, that's pretty fast. What technique are you going to use? Well, we've got a constant acceleration, right? So what does your brain scream when you see a constant acceleration? You should be always thinking kinematics. So we're going to use our kinematics expressions for that. So I want to find the time to get to a final velocity. So which expression do I want to use? Well, I want VF is VI plus acceleration times time. VI in this case is 0 because we're starting from rest. So the time required is going to be VF over A. I'm sorry. And right. So this is our VF right here. So we've got everything that we need and we're ready to go. Let's go ahead and plug this expression in here so that we can all do it all in one piece. And so this is going to be M times C over times VF divided by 2IA. All right, and so now let's put in our data. And we're going to find that T is going to be equal to 25,000 kilograms times 3 times 10 to the 8th meters per second times 1e3 meters per second. That's our final velocity there. And we're going to divide that by 2 times 1360 watts per meter squared, because we're going to have to get rid of our meters here, right? And then our area is going to be 1 square kilometer, which we figured out was 1e3 times 1e3. And when you do all that, you should get that you get 2.76 times 10 to the 8th seconds. Okay, well, that's kind of hard to understand how long that's going to be. So if you keep dividing by, divide by 60 seconds will give you a minute, divide by 60 minutes will give you an hour, divide by 24 hours will give you a day, and you'll find that you will reach this fairly decent speed in about a month. So about 32 days. That's not bad. 32 days and you're already at a kilometer per second, which is a significant velocity for a spacecraft. But remember that when a spacecraft is traveling through space, it's burned all its fuel. Its engine is done. It's just waste matter at that point. It's just slowing the ship down. So in this case, though, that sail is continually providing an additional acceleration. So the engine is running all the time. So this is just a start. After 32 days, we're already up to basically approaching our interplanetary spacecraft speeds. But then we're going to keep building up to where we're going to be the fastest thing alive out there. So this is all possible only because light does act as a particle. It does have these particle type characteristics. So this is basically your introduction to quantum mechanics and gives you an idea of why quantum mechanics itself is so interesting. And also, hopefully you understand why quantum mechanics is only about the realm of the very small. The reason for that is once that de Broglie wavelength gets large, then there's no way that you're going to be able to observe that wave-like phenomenon. So quantum mechanics is weird, but it's very interesting. And it's kind of counterintuitive to a lot of what we understand, on the physical world, because we as humans can only experience this macroscopic world. But the start of a journey into looking at this quantum strangeness begins with understanding the difference between matter waves and photons. We'll see you next time.